Okay, so hello everyone. So let's have a quick introduction for the Professor Michael Kaess. So Professor Michael Kaess' research focused on the efficient inference at the connection of linear algebra and the probabilistic graphics model for 3D mapping and localization. He has previously been the research scientist and postdoctoral associate at the MIT with the Professor John Lerner's Mind Robotics Lab. In 2008, he has received his Ph.D. in computer science in the Georgia advised by Frank Dallett. So welcome to the Professor Michael Kaess, and he will introduce topics on the learning for sonar and radar SLAM.
All right, thank you very much for the introduction. Today, similar to Ayang, my group is working on some non-conventional sensors such as sonar and radar. And so today I want to talk about these two specifically. So sonar, why do we want to use sonar in the first place? So if you have worked with any underwater robots, and unless you went to coral reefs maybe, you probably ran into issues where you couldn't see much. Visibility is pretty low using cameras. In some of the environments that are really relevant for robots, near shore and harbor environments, you essentially have to almost run into an object before you can see it. So maybe at a very short range, if you get close, you can use cameras, but for anything else, this does not work. So this means we have to revert to acoustics. That's basically the only thing that works underwater. And there's some pretty good sensors around nowadays, multi-beam sonars that also work with high frequencies, so they can work in short range and give you pretty high resolution, so tens of meters. But you can also look far out if you want with lower frequencies, and you can look out for kilometers with that. So sonar is really the mode of choice underwater. Nothing else really works. And radio also doesn't propagate, so we have no GPS. So we really have to use that to also do localization. Okay, what are the challenges with using sonar? The first problem is there are no good features or descriptors. So if you try to do SLAM, the community is relatively small for sonar, working on sonar. And if we compare this to the vision community, it took decades to develop good feature detectors and feature descriptors. So the question then is, how can we do this? Of course, in the vision community, recent learning methods at least get to the same level or outperform traditional classical methods. So it doesn't make much sense for sonar to go through this process, which is do learning right away. But that gets us to the second challenge. There are no large data sets available. Right? In computer vision, huge amounts of data, learning is relatively easy. Here, we have to develop specific methods that can work with the little data that is available, maybe use post-supervision, so similar ideas than have been used on the computer vision side. The next challenge is sonar geometry is different. So we have to account for that it's still a projection model, same as with a camera, but instead of losing the range information, you're losing the elevation information, basically the Y coordinate in the image. So an image does contain range. So each cell here corresponds to a certain range and to a certain bearing angle, but the elevation angle is unknown. So any object along an arc within the aperture of the sonar will project to the same pixel. And even worse, if there are multiple objects along this arc, the intensities will add up. So this is very different from the computer vision case where we work with rays. And we can adapt computer vision methods, basically similar ideas to structure for motion. This is now pretty old work that we did a number of years ago, where we extract features, correspond them, and then set up an optimization problem that instead of doing bundle adjustment, it basically adjusts bundles of arcs to get the geometry. There are degeneracies in this that have to be taken into account. So this was one of the main challenges. but this can be formulated in the right way in the optimization so that we don't actually recover necessarily the full 3D position of landmarks, but we still get the full benefit of their measurement in terms of localization. So these methods work quite well, but they have a limitation. You need to detect features. And how do you do that? So the community went through basically all of the computer vision features, and there's really only one that works, that makes sense in this case with these very noisy sonar images, and that's Kaess. And it works decently well, but it's kind of challenging. So you can see here correspondences before filtering from Kaess. We also used Superpoint and LightQ, some learning-based methods, and that also doesn't perform very well. And so our method here that's specifically trained for the sonar geometry and takes into account that the viewpoints change. As the viewpoint changes, the geometry, the image changes in different ways than for cameras. Excuse me, I'm getting some echo here when I'm talking. Maybe if someone can mute, that would help. Okay, so, all right. So basically, computer vision approaches don't directly translate, but we can do similar learning methods than have been used in computer vision. So taking into account that we don't have a lot of training data, we use a method that uses camera pose supervision. So if we can get ground truth for the robot pose, then we can use that to supervise the correspondences. And so in the computer vision side, this was done by exploiting epipolar geometry. And there's something equivalent for sonar images. In the community, it's known as epipolar contours. It's a bit different from epipolar geometry that you're known. It's basically projections of arcs into another sonar image. And what you end up with is a small curve along which a corresponding feature has to lie if you know the relative pose between the two sonar images. And so with this, we can define losses, cyclic and epipolar loss, and we can do training. And so the resulting method performs quite well. Here's a simulation environment. This is using HoloOcean underwater simulator with a somewhat strange environment and above water environment that's been kind of flooded for this, or we simulate sonar in there. And on top, you can see Kaess features, again, before any filtering. So the correspondences are not so great. This is what we've been relying on so far to make it work. But you can also see there are not many features in the first place. So that makes this really challenging to get good results. And so with ours, we can get some pretty good correspondences. There's still some wrong ones in there, but again, this is without any filtering. And this is, of course, with simulation. So we also had to do this in real setting. This is in our test tank. We have a couple of objects on the ground to get some interesting features. And on the right, you can see from different viewpoints the sonar correspondences compared to a first image here. Now, this image actually does include rotation. So there are, the vehicle rotates, even though this is not obvious. It's not obvious because this structure up here looks always the same, but this is actually an artifact from sonar imaging in the tank. That's basically from echoes inside the tank. So the rotation of the sonar is also changing. And you can see this in the correspondences that they kind of shift across. So this performs quite well. This is kind of the first time we really have decent features and correspondences to work with, which makes localization much easier. So here we're comparing numerically our approach, Sonic, to the Kaess and LightQ alternatives, and simulation and on real data. On the left side, you can see inlier ratio, so significantly better here. On the right side, you can see a relative pose error, and this is based on using these correspondences for doing acoustic bundle adjustment. So there's basically the acoustic structure for motion, the optimization back end of that using these features. And again, this significantly outperforms what we could previously do. So this provides localization for the robot. Now the question is, the sparse features are not useful for navigation, so can we do dense mapping of the environment from this? And so dense mapping with imaging sonar is a quite challenging topic we've been working on for a couple of years. And we finally, using learning approach, got some quite good results here. So here's a test structure that we used in the tank. We're not looking at simple geometries here, but more stuff that you would find in infrastructure. So there's more complex topology. And so what we did is basically a north-based method, but adapted to the acoustic geometry. And so what we do is we represent 3D surfaces as neural implicit functions, zero level set. Then we define a differential renderer. This is really the key, modeling the acoustic spherical wavefronts. So you can think of acoustics as wavefronts emanating from a certain point, but you can also in the propagation at any given point do the same thing again. And from there, it's again a spherical propagation of the wavefront. And so with this model, it's possible to define this volumetric differential renderer. And then finally, we need some regularization to get good surfaces as usual with NeRF models. And so the image formation model differs a bit from the vision case. The first thing is we have to integrate over the elevation arc. So it's not just along the ray. Then we have to account for spherical spreading. So that's different, not array again. And then the transmittance is a bit different, but that is a well-known quantity. And so one of the things that changes in NeRF, you would sample along a ray, but in this case, it's really a slice through space that we need to sample from. We basically don't know where along the slice the feature lies, and therefore we have to sample from that and then sample along a ray. So this complicates things a bit. But if we combine this then with the regularization, both an iconal loss and another regularization loss, we get quite good results in the reconstruction. So here's a simulated sonar. There are ground truth objects on top. We have belief propagation and ADMM. These are the previous state-of-the-art methods. ADMM is something we developed in-house. And our method can be shown at the bottom. So if you haven't worked with Sonar before, these are really awesome results, right? You can actually see what the object is in this, and you actually have quite some details available. So this was quite surprising. But again, this is simulated data. So we had to do this in real experiments. Here's again the water tank with different test objects, including this structure was used. We got a ground truth mesh from that object using laser. And then the results can be seen here. The difference to before is that the columns here show different kind of sonar. So one is using 1 degree opening. So this is basically a bit more like a laser range file as a profiling sonar. That's relatively easy. And previously we could solve that. We got the right topology. But with a more common imaging sonars with larger aperture, previously the topology could not be resolved. And so our reconstruction here in all cases gives us the full topology of the object. So this is quite some progress here. And yeah, so with this, I want to switch to a different sensing modality, which is radar. So this seems very different, right? We're going from water to air, and from acoustics to radio waves. Seems like this is completely unrelated sensor. It's actually not. So millimeter wave radar is very similar to imaging sonar. It's a phased array. So this means you have an array of transducers, or in this case, an array of antennas. And with that, you're determining the direction from which energy gets reflected back from the environment. And so this allows to get the bearing angle. For this specific radar, TI radar, cascaded millimeter wave radar, which uses 4 chips that are typically individually used for cars, for example, for collision avoidance. With 4 of these, you get more antennas and therefore better spatial resolution. And so they distributed them so that you get most of your resolution in bearing, but you also get some resolution, some resolve in elevation. So it's really a 3D radar. So there are no moving parts, completely solid state, works with or without light, in bright sunlight or with no light. And it also works through smoke, as Ayaan mentioned previously. So that's a very interesting sensor. Theoretically could be very cheap in the future. I mean, they are commercially being used as individual chips for cars. One thing that is different to Sonar is it does provide Doppler velocity. So you actually get velocity measurements at the same time. Theoretically doable with Sonar, but the Sonar sensors that are commercially available do not include that, and the resolution will probably be fairly low. So here, because of the really high frequency compared to Sonar, you can get much more information, but it's still very noisy. There are artifacts because of the phased array. So it took us a while, and it turned out my original idea of using the Sonar-based methods on radar did not work out very well. So we went back more to classical approaches, and we came up with a way to do radar inertial odometry. And that means we combine an inertial sensor with a radar. And with this, we can walk through a building and get a pretty good trajectory, as you can see from the features, the radar features that are being mapped here. So you can actually see basically the shape of the building also. This is only doing odometry, no loop closure. You can see some duplication of walls here. We've also done loop closure in between, but this here shows you that the drift is actually quite low in this. So it's a quite competitive sensor compared to laser or vision, not completely as accurate. And of course, the mapping is not as good because it sees different features. In fact, it sees the structures inside walls, and it also sees through walls. So you get some structure behind, but you also get artifacts from reflections. So there's definitely work to be done on the mapping side. Now, this works very well here, but there's drift in Z direction in the height. And if you try to do this in a staircase, it actually fails. You have very quick drift. So we determined that this is because the low resolution and elevation. And so our workaround here is to use 2 different radars, 190 degrees off. And in the future, I think there will be radar systems around with antennas equally spread in both directions. That would solve this, but the current workaround is to simply use 2 of these and have them operate at different frequencies, right? So we actually have to reprogram them. They are typically for outdoor environments, long range, and not very good resolution and velocity, but you can reprogram them for shorter range and get good velocity resolution, Doppler velocity. And then also use 2 different frequency ranges for the 2 radars. And so with this, we can here go, including stairs, go through an environment back and forth, and we have almost no drift over that course. Another couple of sequences, different environments, including even a spiraling trajectory here, stairs, and just normal hallways in between. And so all of this works quite well. We can evaluate this against ground truth, or actually visual inertial or lidar inertial odometry, in this case visual. And here you can see if we just use the horizontal in green, we get significant drift in elevation, tens of meters. If we rotate the radar, so vertical orientation, we can get rid of that drift, but now we have drift in X and Y. And so with the dual configuration, we're basically getting close to the visual inertial solution, and we get pretty good trajectories out. We can also do mapping with this. So we can extract features from the radar Again, we did a learning-based approach initially that didn't work so well. I'm not completely sure yet if that was us not doing the right thing. But so we went back to classical methods. So we are using C4 here, which is a typical radar feature extractor, radar target extractor. And with this, we can map stable features in the environment. Now, of course, these are not dense surfaces, right? So this is one thing that's missing. And there's a question, is there enough information in the radar data? My feeling is there may be, right? Not everything reflects as well, right? So surfaces are a bit less clear. But I think there's a lot of data in the radar that we have not exploited yet. And this is clearly a place where learning will have to come in. It's completely not clear to me how classical methods could deal with this. So in summary, I talked about Sonar, learning correspondences, neural dense mapping, both learning approaches. The neural dense mapping I really like because there isn't a generalization issue here, right? You're not pre-training anything. You're just throwing the data at it, the images, and you get a 3D model out. So it's basically an optimization method using a compressed representation of the geometry. That's one way that I'm thinking about this. For radar, at the moment, mostly classical methods. I think this has to evolve a bit, especially dense mapping really has to use learning. And in case you're wondering that I didn't talk about backends at all, I will. I have another 1 or 2 slides. I think I still have a minute left. That's mostly classical methods. So what we've used here are all classical backends across for Sonar and radar. And there are further developments in that direction. So recently we published a robust backend that you may want to take a look at. This is based on graduated non-convexity from MIT, which is a batch method. And so we incrementalized this. We basically combined this with ISAM. So now you can have a robust solver in ISAM that is beating all the other robust solvers for incremental approaches, which are different from the batch case where you have all the measurements ahead of time. And a few other recent developments that are not published yet but will appear soon. One is on distributed smoothing and mapping. So asynchronous, so especially if you're underwater, very unreliable acoustic communication, low bandwidth, targeted to that. And we can exchange as little information as possible and get, and also no information if there's no connection. And we get basically the best solution we could under these conditions. And one place where learning does come in again, but more traditional in terms of optimization, we can actually tune sensor models automatically. So learning covariances in a way that is safe so that you don't get covariance matrices that are rank deficient, for example. Okay, so with this, I'd like to end the talk, and I'm happy to answer any questions that you might have.
Hi, Professor. I have a question.
Yes.
Since the traditional radar sensor cannot capture accurate z-direction information, and I think your proposed, which is a dual radar, this approach pretty interesting. I'm wondering, have you tried or considering utilize the 4D radar sensor, since it can relatively capture some accurate vertical informations?
Which sensor specifically?
4D radar sensor.
Yeah. Oh, yeah. So it's typically currently a compromise between, right? So for the TI radar, they decided to put most of the antennas in the bearing direction to get as high resolution as possible. So it's equally possible to distribute these antennas equally. So you're basically losing some spatial resolution in bearing, but you gain the resolution in elevation. And so, yeah, with that sensor, you could they are not completely there yet, I think, in terms of resolution, but I think that will soon be the case. And with that, you would only need a single radar. So you could do this right now. If the antennas are equally distributed, you're just losing accuracy because you don't have the angular resolution that the TI sensor has in bearing right now.
Oh, I see. Thanks for answering.
And so
thanks
these,
for
go ahead, please.
Thanks for sharing such interesting contents. And I think that's all for this workshop. I want to say thanks to all the speakers to sharing cutting edge and also inspirational contents and works. I also want to say thanks to all the audience, no matter virtually or in person. Thanks for participation. Thank you. Hope you have a nice day. Oh yeah, sure. Let me check. Michael, you mean Professor Mike?
Yes, still here.
Yeah.
Okay. Hi, Professor. I just have one question.
Sure.
With this latest paper, you're doing the learning covariances for estimation. Because I'm working on bi-level learning. I saw your paper on archive. I just wanted to know if you're planning to release a source code for this one soon.
That's still in the works. I'm actually not sure what Mohammed's plan is on releasing. So oh yeah, since you saw the paper on archive, maybe best to shoot an email to Mohammed.
Okay, I'll just ask him. Yes, because
Yeah.
I'm looking into this, and this one covariance for state estimation, which can be used for uncertainty too. I'm very interested, so I'll just shoot the email. Thank you.
Hey, Michael.
Okay. Sounds
It's me,
good.
Daniel.